There we go. Recording in progress. Okay, so where we're at is we have the IOP, that's Hyperplonk. And if we even, I think it often makes sense intuitively to divide that into even smaller chunks where you have the arithmetization and the zero check. So if we just focus on that now, you have the zero check that is essentially a sum check. And then that's an IOP, and we need the polynomial commitment scheme to basically just check that the prover, which acts as an oracle, has behaved correctly within the rules. So we need to make sure that two things are correct using this polynomial commitment scheme that we will soon define. One of them being this, that the last message from the sum check protocol, which is based on random elements from the verifier, needs to be consistent with the constrained polynomial evaluated at the witness polynomials. And the second thing we need to be true is simply for A, B, and C to be multilinear polynomials. And the latter point is fully doable with something called tensor FRI, which just extends FRI to sort of the multi-dimensional realm. The first point of checking consistency doesn't work with that. And to see that, the element R is very unlikely to be in the evaluation domain that we pick. So that kind of doesn't work. That goes out the window, hoping for just crossing our fingers and hoping for that to be true. So that doesn't work. So we need something else. I think I'll go to the next page because I want to prove this too. So credit for this should go to my supervisor, Jonathan. All right, claim. I should have written proposition. It's a bit long. Okay, so, first we have the map. We'll call it phi, which goes from I think there's an additive group of, we'll just write multilinear polynomials to there's also a group, there's not a ring, right? Yeah, to the group of, no, this should be strictly less than, of polynomials of degree less than 2 to the power of d. And the map is, we simply extend linearly the map that sends a x0, I0, x, oh wait, not 0. Let's do 1, because we've already done it so far. Okay. Maps that to ax. So, we just view it as a binary decomposition, ij 2 to the j. And the inverse is defined by axk to a x0, I0. Oh, sorry. Normally I write 0. I normally do 0 indexing, but now I've kind of committed to this. So where, that's right. I think in Hyperplonk they write this for binary decomposition. It's equal to, again, I should just skip to 0 indexing. Okay, so yeah, it's just switching between the standard representation base 10 and base 2. So that's an isomorphism. Okay, so the kind of unexpected result, I guess, is, and this is our actual claim. All right, actual claim is that for f in, so f is multilinear, something like that, yeah. And any R1 through RD field elements. And let's say the final message of FRI on, it's kind of, I guess it's, you can understand what it's a bit, how should I say it, imprecise, but you can understand what I say when I phrase it like this, right? With the verifier messages R1 through RD is F of R1 through RD. Okay, what this is essentially saying is that the inverse of psi is essentially, you know, FRI yields the same result. FRI is essentially computing this just at this point. And we're going to use this. I'll sketch out a little proof because this is non-obvious. At first, I didn't prove it. Jonathan and I were just in his office, and I was like, "Is this true?" And he was like, "Yeah, I think so." And then we tried out with an example, and he kind of convinced me. But I've kind of sketched out a little proof. So we'll do it by induction on the degree n equal to degree of phi of f. So this is a univariate polynomial. Okay, so then we have ax plus b sent to ar0 plus b, and this is simply f of r0. So induction step n to n plus 1. I'm just gonna sketch this out. So you have phi of f of x. We do one step of FRI to get let's write this 0 x plus r. Here I am again with the 0 indexing. F1 of x. And then you can kind of see with induction how this works now, I assume, because f0 and f1 already have smaller degree than n, so we can just essentially use the induction hypothesis. So this thing and this thing, they're going to be equal to some f0 and some f1, so that f is equal to, you know, and you can always decompose multilinear polynomials in this way too. RD plus R2 plus R1 times F1 R2 RD. Okay, and then that's proven by induction, essentially. Bit quick maybe, but the point being, this works. So if we go back here, the maybe surprising way that we can commit to these polynomials is by first converting them to univariate polynomials in this way. So we this should be up here, by the way. Commit to phi of A, phi of B, and phi of C. And then we run normal FRI with a small twist, which is that, you know, normally in FRI, you decompose into two different terms, and then you add some randomness. In this case, it's not random. We simply use a messages from sum check. And then what we end up with at the end of FRI we then have A of R1. Actually, we simply write the vector B of R and C of R. And moreover, you know, the last check of FRI will And this is going to be after a logarithmic number of rounds, right? Because remember, we go from the multilinear polynomial to the polynomial that is exponential in the number of variables, and then we just go back to the logarithmic one. So you know, it has the same number of rounds as the number of variables here, namely d. And once we have these things, the verifier can check herself that you know, this thing holds as we wanted to. And at the same time, she can check that A, B, and C are they should be constant, or rather, at that step of FRI, there should be a constant output. And she can check 2 with 1 essentially with this test, and that is that sums up the proof. So just to get to the added complexity, so we'll just add verifier time should be total is you have.
Sorry, Ollie, what was that?
Yeah.
What was the last bit? Yeah, in the last step, we need to check it's constant, right?
Yes. So essentially, to check that A, B, and C are multilinear is equivalent to checking that phi of A, which is this constructed polynomial here,
okay,
is constant after d rounds of FRI. Does that make sense?
Yeah.
I had a question on this. I think I see how it works if the prover is honest, but given the sparseness of the checks we do in FRI, do we really know that the evaluation is correct?
Sorry, which evaluation?
Can the verifier really trust that the last prover message is the multilinear evaluation of the polynomial? So
first, the prover and the verifier engage in some check, right? And then the last message from the prover there is this P of R, right? And then but before that, before engaging in that, by the way, the prover is already committed to these polynomials. So the kind of course of action is first commit to the polynomials, then engage in the IOP, and then check at this random point that the equality holds. I'm pretty sure it's sound, but what is exactly your concern?
So like on the other side, it seems like we're using FRI as a multilinear to prove the evaluation of a multilinear polynomial, right?
We're using FRI to prove that the univariate polynomial we've committed to isomorphically maps to a given multilinear polynomial.
Is it correct to think of it as an opening argument?
Yes.
We're okay. Like we're taking a univariate polynomial and kind of reinterpreting it as multivariate, and then opening it at this vector.
Yes, right? I think that is accurate. Yeah.
Okay.
So yeah,
but it seems like the final message should be the evaluation of, it should be exactly the evaluation of this polynomial at this vector R. But like in FRI, usually the prover has some flexibility to, they can introduce a few errors here and there that are not that likely to be detected. So I'm just not sure how to convince myself that that the last message will be exactly correct here.
What do you mean by correctness? That the last message will actually be like A of R, B of R, C of R, or what do you mean?
Yeah, how do we know that the prover folded this polynomial correctly based on the components of R. There's the query phase, of course, which sort of checks that the folds were correct, but it has a certain error margin, right?
It does have a certain error margin, but that can just be removed by running it a certain amount of times. No, like I think the soundness error should be on the order of FRI, but the way you solve that is just by kind of repeating the query phase many times, isn't it?
Yeah.
Picking out different points from the evaluation domain and kind of running through.
I'll need to think about it more. Yeah, maybe you're right though.
I think this is sound, and the thing that I think the most important point there is that phi and psi are actually isomorphisms. So what that means quite literally is that committing to the univariate polynomial is equivalent. It's not roughly equivalent to, it is absolutely equivalent to committing to the multilinear one. I think that is, I think that's an important claim, because here, you know, we're committing to phi of I, phi of B, phi of C, but there's really no difference between doing that and committing to the polynomials themselves.
Yeah, I see what you mean, but like normally in FRI, the verifier isn't necessarily convinced that the constant at the end was the correct result of, you know, every fold being like doing all of the proper folds. Usually they're only convinced that there's some kind of proximity, like the original function had, the original list had some kind of proximity to a Reed-Solomon code word.
Okay, but in this case, then we demand it to be exactly the, I guess the question then is, could the prover fold it incorrectly and arrive at constant values which also satisfy this equation? Because that equation still needs to be satisfied, right? That P of R is equal to C of A, B, and C at R. So that is like the additional constraint that's being put on this. So that is true that FRI is really just a proximity test, but I think in this case, and yeah, that is true that it's something that certainly has to be explored more formally. But I think it should work.
Okay, thanks.
So yeah, okay, so just to get on to like some time complexity, the prover time is linear for Hyperplonk, obviously, and it is linear for FRI. I'm not sure how the constants compare to KCG, but that might be a bit worse because you're evaluating over like a big. I'm not sure. Do any of you guys know?
How the constants compare?
Yeah, in the prover constants for FRI versus KCG.
For us, typically interpolation isn't really the main bottleneck. Typically, Merkleization is the main bottleneck in FRI. But I think it's a bit different for each implementation.
Yeah, I mean, I would assume, but you're not interpolating in FRI, right? Like we were discussing this.
Yeah.
Like I don't. Maybe I'm misunderstanding, but what do you mean by interpolation exactly?
Oh, yeah. Sorry, maybe I shouldn't say in FRI. Yeah, I guess you could say it happens before we start FRI.
So you mean interpolating the witness into like the witness polynomials?
Yeah, or given a polynomial in either form, there's some sort of blow up that happens to get to a code word, right?
So you mean evaluating on the evaluation domain? Okay, yeah. Okay, so Merkleization takes longer than evaluating. Okay.
Yeah, I think it really depends a lot on how clever our FFT implementation is and how large our caches are and all of that, and what hash function we use.
Yeah.
Yeah. Sorry to to interrupt.
No. I mean, I asked the question. Yeah. Okay. But yeah. So just to get to the asymptotics, I'll write it like this because I think that is nice. Where this is Hyperplonk plus log squared and FRI is equal to, basically we get polylogarithmic proof size and verifier time, and then we get linear prover time. So this is quite nice. And yeah, it is a well-formed question. So another thing about FRI, right, is that normally the verifier sends random challenges, and in this case, they're not random. So I think it is fair to ask questions about the soundness assumptions here. But yeah, intuitively, I think it's very difficult to cheat this. Yeah.
So I missed the start. Why is the verifier not sending random?
Okay, so the messages here are first the prover and verifier engage in some check, right? And there the verifier sends random messages to get messages back that are polynomials, and so back and forth in that way. And then the final message from the prover is this polynomial P evaluated at all of the random messages. So they're random there, but then when we compute, I guess you could call it an opening proof here, as Daniel did, or check that this equality holds. When we use FRI for that, they're kind of no longer random in the sense that they're known to the prover before engaging in FRI, but it's not like the prover has picked them out, right? Like the prover first commits to the polynomials, then the verifier sends the messages and they're random at that point, and then they engage in FRI. So, you know, I think cheating this is really, really hard. But I don't have any like formal proof on that. Okay, so I think this is interesting for I think it's interesting for a few reasons. Like, first of all, the Hyperplonk part of it seems to me in general to be a strict improvement over normal Plonk. And then the only annoying thing about using Hyperplonk with KCG is that the kind of nice thing about KCG proofs is that they're constant size, and then because you have some check, there is a logarithmic term to it, which is a bit annoying. So for us, where FRI has relatively big proofs and the sum check add-on to that is not really significant, and there's the opportunity to use custom gates, which which I mean should have like quite big ramifications, I would imagine, because it just allows you to have much more complex expressions as gates. All of this makes me think that it is an interesting combo, that if it is sound, it should offer really good performance.
I have a basic question. I've only seen like theoretical descriptions of some check, so just wondering when we really implement it, like the prover is sending these sort of partially even these polynomials where some of the variables are fixed and some of them are free. Does that mean like if does that mean like each round of sum check we send I guess in this case it would be a separate Merkle tree with a different different multivariable polynomials, and then at each step one of the variables becomes fixed, so the size of our polynomial we're committing to is halved?
So during sum check, it happens in the following way. So first, the prover sends a message that's like, hey, this thing P is equal to tau. In our case, tau is 0. V sends back some variable, and then I have to see that I remember correctly, but I think essentially what the prover does then is the prover only sends univariate polynomials, because what you do is it's something like P of what is it, like R1 then X, and then what you have is all of these. It's a sum to shit. I should remember this, but I don't.
Oh, right.
Well. But you send these sums where basically the B's are these like binary values that you have in the beginning, and then you slowly introduce randomness, so that this is like, call it P1 of X, and all of these are univariate, and the verifier can check themselves that the messages are consistent with one another. Check that iteratively. And then, you have some message pi I of X is equal to the sum of like pi at R1 to Ri minus 1 X bi plus 1, and so on. Does that make sense?
Yeah, I think so. Thanks.
Yeah. So what we get just by doing this, right, is the X gets pushed further and further to the right, and the final message is then something like PD of X is equal to simply yeah, it's I don't think it's even a sum anymore. It should simply be like something like PD of I minus 1, which is a univariate polynomial at RD, which again is equal to this thing. So yeah, that's how it goes back and forth.
Okay. And then one other question. So with this sort of variation on FRI, is there any blow up, or is this more like FRI not with a code word, but just a variation on FRI where we don't need to blow up or map to a code word?
That's an interesting. No, I mean, I would imagine for the commitment, you're still like Merkelizing it, so you're still committing to the code word. So I think the code words are not to escape, because you need to commit to these polynomials in some way. Yeah. No, I think it is essentially like standard run-of-the-mill FRI, but just with the messages from the verifier kind of being fixed.
Okay.
Yeah, so definitely so at first here, when you commit it before sum check, you do have to evaluate it on this like massive domain E, and then compute the Merkle tree and do all of that, and then shrink it. Is that what you were asking?
Yeah, thanks. It's interesting to compare it to the transformation in Hyperplonk in Appendix B, I think it's sort of the same approach of like reinterpreting a univariate polynomial as a multilinear one with the same coefficients. But they rely on some kind of separate opening argument for univariate polynomials.
Yeah, they actually have. They do have some FRI stuff here. Yeah, the FRI base.
Yeah, they have a way to support FRI, but it involves kind of like this black box FRI based univariate PCS.
I think this seems to be essentially this. I think. I'm not sure.
Yeah. But I think their approach would still involve FFTs because, you know, if we're saying we're going to build a univariate PCS based on FRI, then normally that involves, you know, a blow-up factor with a low degree extension.
Yeah, there are FFTs involved here as well, though. But it's so the prover time is linear because I think it is something like it's linear in the degree of the univariate polynomial, but then you have the size of the evaluation domain, and that essentially gets translated into the FFT cost. So I think it's like kind of cheating a bit in that sense.
Okay, so there are FFTs here.
Yeah, I mean, if you look at the original FRI paper, and obviously there are FFTs in there being used. They you know, they say linear prover time. So I think
yeah, I think if we already have a code word, then the rest can be linear. But normally, just to get a Reed-Solomon code word, normally we interpolate for that, right?
Yeah, but to get that, we have the normal the polynomial and then evaluate it on like a big domain, right? And we use FFTs to quickly evaluate the polynomial on the domain. Is that not it?
Right. Yeah.
So in this case, we still need to do that because we only have the polynomial. So we need to first evaluate the polynomial, the univariate ones on the like initial FRI evaluation domain.
Okay. Yeah, that makes sense. So would you agree that it seems like with FRI we can't avoid using FFTs and getting a logarithmic factor?
Yeah, but so I do agree with it, but just that the logarithmic factor seems to be absent from like you do have to do FFT, so there must be some logarithm in there, but I wonder if it's like a logarithm of the evaluation domain size or something like that instead, because yeah, FRI is, you know, presented as a linear time thing. But I agree with you, like there's no way of getting around FFTs in that case. So it will probably be less prover efficient than doing KCG, I would imagine. But the way that I compare it, you know, to something like say Plonk 2 is you can kind of modularize it, right? So Hyperplonk seems to me to be better than Plonk for some of these things. So even if FRI is no better, if it's just the same and you do have a small additional cost from the sum check, but that is really very small. I do think that this should still be more performant intuitively than Plonky 2.
Yeah, I think the aspect of better, cheaper, high degree constraints is very interesting. I'll have to think more about what sort of things we can do with that.
So there is obviously like everything up to FRI is linear, whereas in Plonk, every Plonk based protocol, you know, everything up to like the last bit is n log n. So there is some efficiency gain there.
Hmm. Yeah, you're probably right. I think different Plonk implementations handle it differently in terms of like at what point do they interpolate?
Okay.
Like, and how they handle the quotient. You know, do you compute the quotient in evaluation form, or do you do long division or something?
So do you guys at zero, do you wait to do the interpolation until basically you evaluate it on the evaluation domain and then go directly from witness vector to commitment?
So for us, we do low degree extensions of everything up front. So all of our witness polynomials, we immediately take low degree extensions of each one, and then our LDs are on a coset, like we discussed a bit, so that we can compute the quotient polynomial in evaluation form without dividing by 0. And then I guess there's a bit more FFTs once we have evaluations of the quotient polynomial, because it's we have to split it into 2 halves. So since it's like more than the degree of the other polynomials.
Okay. But you do interpolate the witness polynomials first, like at the very beginning, before you do any, because you need that for the 0 check and stuff, right?
Yeah, exactly. Yeah.
So and for a permutation check, you essentially you do need to do polynomial interpolation and get some polynomials early on. And what I'm saying is, with Hyperplonk, you still need to do that, but multilinear interpolation is faster than univariate one, like FFT based one, and therefore there should be some efficiency gain in that part.
How does multilinear interpolation work?
Okay, so how that works is you have say B1 through BD. We interpolate over the Boolean hypercube, right? And then we have some F, and then call the low degree extension F tilde of simply X vector. And then what we do is very simply we take the evaluations of F over the Boolean hypercube, and we multiply this by this EQ polynomial, which
right.
is yeah, like this. And I believe the way you can get this linear, so the canonical way of doing this, I believe, is still n log n, but there is a section in Justin Thaller's book on how you can essentially use dynamic programming to make this sum, to compute this sum in linear time.
Oh yeah, I sort of vaguely remember one of the GKR papers mentioning that, I think.
Yeah. that's it. And you know the form of the EQ, right? It's like this product of like bi xi minus 1 minus bi 1 minus xi, and then the trick is, you know, all of these are bit values. So if say bi is 0 and xi is 1, then both of these terms are going to be 0, and thus the whole product evaluates to 0. So it really shows it. And on the other hand, if all of them are the same values, say bi and xi is 1, then this term is 1, and say they're 0, then this term is 0. So it measures equality on the Boolean hypercube, which also shows that this is one extension of it, right? Because for every element on the Boolean hypercube, f tilde of, you know, b is equal to f of b, because all the other terms are valued to 0.
Yeah, makes sense. So then would we like pre-compute the coefficients of EQ, and this is to get to coefficient form, or?
Yeah, I'm not. Yeah, so this is in. I did see this in Justin Thaler's Bible, but I haven't. I don't recall exactly how it's being done, but there is a way of doing it in O of n, and I believe the constants are not. I like, it is significantly more efficient than FFT based interpolation.
Okay.
Yeah. So I just think that those two things, and maybe in particular the custom gate argument, but you know, I know very little about the actual implementation details of recursive proofs, so you would be much better positioned to say if if there are any high degree expressions that are used regularly that would be valuable to have a custom gate for, but which isn't possible with say Plonk style arithmetization.
Yeah, I think there's probably a lot we can do. I haven't really thought through it too much, but yeah, doing more range checks, much more efficient. We can sort of batch range check if we have high degree constraints, or if we're doing recursive proofs with arithmetic hashes, maybe we could use a very high degree SBox. Yeah, it would be interesting to think more about that.
Yeah. Yeah. So I think it's a direction that is interesting to look at, and really the thing is, because of like the modular nature of these schemes, I think it is fair to say that if this is sound, then it does work. Like, if the question is, as I think, as you were also saying, Daniel, that the big question is, can the prover cheat in some way during FRI by committing to the wrong polynomial, the wrong univariate polynomials, and then still end up with values at the end such that it's going to be really difficult, because the values at the end have to be both constant and they need to fit into this polynomial, this equation here, which the prover doesn't know at the time of committing, right? It's going to be very difficult, I think, to cheat on that.
So what was the kind of order of operations again? Could you
remind me? First the prover commits to, that this should be at the top. So first the prover commits to the wire, to the kind of univariate form of the wire polynomials. Then they go through some check, and the committing is just as Reed-Solomon codes over some evaluation domain. Then some check, and that's where V sends the random messages, and then run FRI on phi of A, on the committed to univariate polynomials, And if the last message from the prover is correct, then output accept, and if not, reject.
Okay, got it. Yeah. So it's like the last step of sum check is the verifier has to evaluate at polynomials at R vector.
Yeah.
And yeah, using FRI as a opening argument to do that, right?
Yeah.
Okay.
That's it. So, normally with normal FRI, the verifier doesn't really care what the last message is as long as it is constant or reflects a constant polynomial. Or rather, the point isn't really what the concrete outputs are. But in this kind of flavor of FRI, it really does matter what the message is. So it needs to be both constant and equal to those values, because otherwise there is a little bit of leeway in the sense that you can change A a little bit and then you change B a little bit so that it still fits. But yeah, again, that's going to be very difficult, I think.
Mm-hmm.
Okay. I guess we can just wrap up. If I don't know if there's anything else I should go through with regards to this. If any of you guys have any other questions or comments.
Where are you going to take this, or are you working on a paper? Right.
I'm not sure. I don't think it is paper worthy, to be honest, because it's, Hyperplonk is paper worthy. It's very novel. This is kind of just taking some things that already exist and putting them together. I think it would be cool to implement it at some point, but I don't think I have the time right now. Yeah.
Because I see what you're saying. It seems like it would be very hard to cheat because you're making the commitments at first. But I think if you were going to try and make a proof,
I might try and formally prove soundness.
Yeah, that's going to be hard to reason about, I think.
Maybe. I'm doing that for my thesis anyway, so I need to get some training in proving good soundness bounds. So I might do it, but we'll see.